Okay guys, today we're going to do page 31 in your notes, Molarity and Stoichiometry. This is the last page of notes in this unit before our test this week. Okay, so let's jump right in. And our first example, so we're going to combine what we know about stoichiometry and what we learned about molarity last week. So our first example says if you have 400 milliliters of a 1.50 molar solution of CaCl2, how many grams of CaOH2 should theoretically be produced? So it's telling you have 400 milliliters of this and its concentration is 1.50 molarity, okay? So it tells you how much you have and what its concentration is, and it wants to know how many grams of this you can produce. So because we're going from one substance to the other, we know it is a stoichiometry problem because it involves a balanced chemical equation where we're going to have to do a mole ratio to go from one substance to the other. And we have molarity involved. So we know, because of last week, that whenever we have a volume and a molarity, we're able to figure out moles based on that. And if you remember from our notes last week, we had that triangle. Maybe I'll write it up here just as a reminder. Okay, where we had moles on top, molarity here, and liters here. Okay, so if I have I'm looking for moles, I cover moles with my finger, I can do molarity times liters, and that will give me my moles. The problem is this is not in liters, is it? So let's convert that to liters. Remember, you move it 3 to the left, so that would be 0.400 liters. Okay, so we know that moles is molarity times liters. Okay, because we covered that with our finger. We did that, okay? And then let's plug stuff in. So plug in our molarity, so 1.50 for our molarity. And our liters are, remember, you can't put milliliters in here. If it says L for liters, you gotta do liters. So 0.400 liters. Put that in our calculator. And I get 0.6 moles. Moles of what? CaCl2. That's important. Okay, so keep track of your substances. So this is how many moles of CaCl2 we have. We need to figure out how many grams of this we have. So we're going to take moles of this, go to moles of that, and then we'll convert it to grams. So let's do that stoichiometry problem. So let's take our 0.6 moles and move it down here, moles of CaCl2, put it over 1, because now we need to go to moles, from moles CaCl2, to moles of our new substance, which it's asking us to find CaOH2, so calcium hydroxide. Okay, and then, but it asks us to find grams of it, so we have to do one more step to take our moles of calcium hydroxide and convert that to grams of calcium hydroxide. Okay? Okay, so now let's look at what we have. We have a mole ratio here. Remember, I like to put a cloud around my mole ratio because it reminds me, hey, this is special. This is where we look at the balanced chemical equation to find these coefficients. So let's look at CaOH2. Does it have anything in front of it? No, it has nothing in front of it. So that's implied to be a 1, right? So let's put 1 there. Let's look at CaCl2. Does it have anything in front of it? No, so that's also implied to be a 1. So let's put a 1 there. That was easy. Everywhere else we see the word mole in a stoichiometry problem, we put a 1. A lot of 1s in this problem. Then G for grams reminds me that I need to go to the periodic table and find the molar mass of this. So in the interest of time, I'll just tell you what I got for the molar mass. It was 74.096. Okay? And now we need to cancel our units. Those guys cancel and those guys cancel. And so now we're ready to put this in our calculator. There's a lot of 1s, which makes it really easy. It's just going to be your 0.6 times the 74.096, and I get 44. So I'll write my unrounded answer first. I got 44.4576. How many sig figs do I need? Well, let's look at the original problem. This had 3 sig figs because there was a decimal there, making it 3 sig figs. Sorry, you can't see it anymore. And this has 3 sig figs. So we need this to be in 3 sig figs. So it's going to be 44 point, this 5 is going to bump that up to a 5. So 44.5 grams of calcium hydroxide. Okay, that's our answer. Okay, so it's not really anything new, it's just taking what we learned about molarity and taking what we know about stoichiometry and combining them into one problem, okay? So our next problem here is a U-try. So I'm going to have you try it. It's similar to the one we just did. The only thing I'm going to point out, it says excess iron 3 nitrate reacts with blah, 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 all this. If it says excess ever, you can ignore the excess. And so let's write that down to have in your notes. Ignore excess. If a problem ever says, hey, you have excess of this, it means you can ignore it. It means you have an overabundance of this, so this is automatically going to be your limiting reactant. It's basically just telling you, it's saving you the step of making you figure out your limiting reactant. Okay, it makes it easier for you. Okay, so solve this problem the same way you did that. Go ahead and pause the video to do that. Okay, hopefully you paused the video. This is what I got from my U-try. First thing you have to do is convert that to liters. And then you're going to figure out how many moles of K2S you have. Take those moles of K2S, go to moles of FeS3, and then go to grams of Fe2S3. And I got 21.8 grams. Okay? All right. So, onto the back. Okay, on the back, here's our next example. It says we have 0.0520 liters, so let's highlight this, of an 8 molar hydrochloric acid solution. And it's reacted with 7.55 grams of potassium hydroxide. It wants to know what is the limiting reactant and what is the theoretical yield of water in grams. Okay. So this is going to take more steps, because remember, if it's ever asking, like, what's the limiting reactant, and it gives you 2 different, like, reactant amounts, you know you're going to have to do 2 different stoichiometry problems. So before we can do any of that, because we're used to getting problems like this where it just gives it, like, grams of one reactant, grams of the other reactant. However, it's not always given in grams. In this situation, it's not given in grams, it's given as a solution. It tells you the molarity and the volume. So we're going to have to do these 2 a little bit differently. But first, before we can do anything, what do we need to write out? A balanced chemical equation, right? Okay, so it says we've got hydrochloric acid, so HCl. I'm going to write it up here to save space. And it's reacting with potassium hydroxide. Potassium is a +1. Hydroxide is a polyatomic ion with a -1, so it's just going to be KOH. And it doesn't tell you what our products are. Uh-oh, we have to remember. Okay, this would be a neutralization reaction. I know it's neutralization because I have an acid and a base. How did I know this was an acid? Because it starts with hydrogen. How did I know this was a base? Because it ends in hydroxide. Whenever you have a situation with an acid and a base, something that starts with hydrogen and something that ends with hydroxide, you know it's an acid-base neutralization reaction. And you know that your products are going to be water, which of course is H2O, and a salt. And the salt is going to be whatever's left over. After you've taken your H and your OH to make water, what's left over? You have chlorine and potassium. So, again, potassium is a +1, chlorine, if you look at your periodic table, is a -1. Oops. So, it's just going to be KCl. Never write CLK. Why did I put the K first? I put the K first because it's positive. The positive thing always comes first. Okay, and it looks like it's already balanced for us. Everything's a 1-to-1 ratio, so that's easy. Okay, so now we have our balanced chemical equation. Let's start off by looking at our hydrochloric acid. It tells us its volume, it tells us its molarity. And we know, because of what we just did on the front here, we know if we have molarity and we have liters, we can figure out moles. So same as the front, our moles are going to equal molarity times liters. So let's do our molarity times our liters, and it's already in liters, so that's cool, we don't have to convert it. Okay, And when we multiply those, we get 0.4 here. 0.4016 moles. Moles of what? Hydrochloric acid, HCl. Okay, cool. So we have how much HCl we have in moles. And it's asking us to find the theoretical yield of water. So let's go ahead and do that first. So we're going to take our moles of HCl we just figured out, HCl, and we'll do a little stoichiometry problem to go from moles of HCl to moles of water, H2O. Okay, but it wants to know the theoretical yield of water in grams. So I'm gonna go to grams. Grams of H2O. Okay, here's my mole ratio, where I have moles over moles. I like to put a cloud around it to remind me, hey, this is the mole ratio, it's special, this is where you look at the balanced chemical equation to find your coefficients. So let's look at our balanced equation. Everything's a 1-to-1 ratio. They don't have any coefficients in front of them, so everything is a 1. So that's going to be 1 and 1, okay? Everywhere else you see the word mole is also going to be a 1. Okay, G for grams tells you to go to the periodic table and find the molar mass. The molar mass of H2O is 18.016. Cancel everything out. And when I put all of this in my calculator, I got 7.235, etc. grams of H2O. Okay, so am I done? No. I found grams of H2O pertaining to the hydrochloric acid, based on how much hydrochloric acid I started with. However, we have another reactant here, KOH. So we need to figure out how much water we would make based on the KOH, and then compare the two. And remember, whichever one's smaller is your theoretical yield of water. Okay, so let's take this. This is the way we've been doing it for a couple weeks now. We take our grams of potassium hydroxide, and we're just going to do a stoichiometry problem where we go from our potassium hydroxide to our grams of water. And then we're going to compare our 2 grams of water to kind of see which one is smaller. So first we have to take those grams and convert them to moles. And then we can do our mole ratio where we go from moles of KOH to moles of water. And then we'll go to grams of water so that we can compare it to the grams of water right here. Okay, my mole ratio is right here. It's where I have moles over moles. Let's look at our balanced chemical equation. Oh, easy peasy. Our balanced chemical equation, if you remember, has 1s on everything. So it's going to be a 1 and a 1. Everywhere else we see the word mole, we're going to put a 1. And G for grams tells us to go to the periodic table. So when I went to the periodic table for this one, I got 56.108. And for this one, same as up here, 18.016. And then we cancel everything. Okay? So when I put all this in my calculator, so I'm doing my 7.55, then I'm going to divide by 56.108, press enter, multiply by my 18.016, press enter. Oops, there you go. You can see that a little bit better. I got that number. So I'll round that to 2.42 grams of water. Okay, so we figured out how much water we would make starting with our HCl. We figured out how much water we would make starting with our KOH. So starting with our HCl, we figured out how much water we produce. Starting with our KOH, we figured out how much water we'd produce. So now we have 2 different answers. Which one is the right one? Well, the smaller one. The smaller one is the theoretical yield of water. So this one is my, because it says, what's the theoretical yield of water? This is my theoretical yield of water. this bigger answer is nothing. We don't care about it, okay? Because the HCl ended up being excess. So we have excess of that, okay? It says, what's the limiting reactant? So remember, your limiting reactant has to be one of your two reactants. And a reactant is something to the left of the arrow. So our limiting reactant is either HCl or KOH. Which one is it? Well, we just decided that our smaller answer, our theoretical yield, came from KOH. So KOH is going to be our limiting reactant. Okay? KOH is going to be our limiting reactant. All right? So in the end, we still solved for grams of H2O with both of them. We just had to go about them different ways because one reactant was given to us in grams originally. The other reactant was given to us in forms of a solution originally. So it's not that one's necessarily harder than the other. You just have to recognize this information you have to use to find moles first. And then you can go to grams of H2O. And then this one, you can go straight from grams to moles and all that. Okay? So that's how we did that one. The next one is a U-try. So on the U-try, before you do anything, you're going to have to write out a balanced chemical equation. Okay? You have to write a balanced chemical equation. And it actually tells you what it makes. It tells you what it makes. So go ahead, write out the balanced chemical equation, and then solve the problem. It's very, very, very similar to the one we just did. So start by writing out a balanced chemical equation. Go ahead and pause the video and do that. Okay, here is what I got for my answer. First, you had to write out the balanced chemical equation properly. See if you got that right. It tells you what it makes. Okay, you just have to make sure you crisscross your charges properly on the barium chloride and balance it properly. Okay, then I took this information. You had to convert to liters first. Took this information to find your moles of HCl and converted it to grams of barium chloride. And then I took my grams of barium peroxide and converted it to grams of barium chloride. And because this one was smaller, that one was my theoretical yield, which made the barium peroxide my limiting reactant. Okay? All right, go ahead and work on the assignment.